Alright, in this lesson we're going to look at radioactive decay, so each of the three, alpha, beta and gamma, and see what actually happens. So when things decay, they don't disappear altogether. So what happens, it becomes a different atom. Right, so we're not having any particles or anything disappeared. And the total numbers of particles, we've still got the same numbers of particles, protons and neutrons. Well, actually it's not quite true. Same numbers of particles, because a neutron can decay to be a proton and electron. So, but in total, the mass and atomic numbers remain the same. So, our mass and atomic numbers they've got a balance. Alright, so on each side of the equation. So let's have a look at alpha decay first of all. So in your notes there you've got this as an example. Alright, there's a couple of examples, and this is the first one. So notice uranium-238, I've already mentioned that decays via alpha, so this is our alpha. So in both cases, so these two things, these are two different ways of representing what's going on. Alright, so let's get rid of those drawings. So it becomes a different atom. So uranium decays and becomes our alpha. So you'll notice our atomic numbers on the left hand side a total 92, and on the right hand side again a total 92. And then when you look at your mass numbers, on the left hand side total is 238, and same on the right hand side, 234 for the thorium and 4 for the alpha particle. Alright, so there's a couple of terms that are used, and the terms are, so this uranium, that's called the parent, so that's what we start with, and then the thorium, that's called the daughter, so that's our daughter nucleus. Alright, so they're just two terms that are used, parent and daughter. And you'll notice this, it says energy, a lot of it's kinetic energy because these alpha particles get shot out. So they have kinetic energy. So overall, what do we know when we're comparing the parent and the daughter? Well, what we notice is that we have a decrease in atomic number by 2, and also a decrease in the mass by 4. Alright, and so you can see that 92 down to 90, 238 down to 234. So you can see that is the case. They haven't disappeared altogether, remember? It's now our alpha particle. So those things are now in the alpha particle. And also, as you can see, that I said before, that the stuff doesn't disappear, it changes into something else. So this uranium is changed into thorium. Alright, there's another example of radium and radon in your notes as well. So if we use a symbol form, we start with X, which has atomic mass and atomic numbers. It decays via alpha 4, 2. It's important, I haven't mentioned this yet, but it's important that this 2 plus goes on there so that we know that it's an alpha particle, not a helium atom. Now they all have energy, all of these. So often you don't see the energy written, but they do. So what happens, right, we get to another atom, another element. So element Y. And what do we know about that? Well, we know its atomic number is 2 less. And we know its mass number is 4 less. Alright, so our number of nucleons is the same on both sides of our equation. Alright, so we've got an example, so let's have a look at the example. Alright, so we've got thorium going to element Y, whatever element Y is. Well, we can figure out element Y, its atomic and its mass numbers. So, total of 90, 90 minus 2 is 88. And the mass number, 232 total, so 232 minus 4 is 228. So we go to our periodic table and we look up what number 88 is, and we see that its symbol is Ra, and so 88 to 28. Alright, so there's our alpha decay. So let's now have a look at our beta decay and see what. Alright, so beta decay, remember there's two parts. There's an electron, and we can write that as this. So E, -1 down the bottom, -1 atomic number, and 0 for in terms of balancing the equation. So no mass, negative charge. Or you can just do it as a beta symbol, -1 and 0. And for our positron, do it as +1 and 0. So no mass, positive charge. Alright, now the positron and the electron, the only difference is the charge. Everything else about them is the same. Alright. So let's have a look at an example. So this example here is beta minus decay. Alright, so we've got our thorium, protactinium plus our beta and energy. So there you can see that E minus 1, 0 for balancing the equation. So again, there's got to be 90 on both sides. That's 91 and that's -1, that's good, and 234. So what you notice, of course, is the atomic and the mass numbers balance. So that's in your notes there in that little red. And then we've got a note. So this particular one is the beta minus. So the electron, it comes from the nucleus. Alright. So what happens in the nucleus is that we have a neutron decaying. So the way we could write that is that it's a neutron, no atomic number, 1 mass. That becomes a proton, H11 is one way we can write that, plus our, oops, wrong symbol at the top there, 0, there he goes here. So that's what's happening. Right, so a neutron becomes a proton, and this electron, and that gets shot out. Alright, in the case of our positron, again that's from the nucleus, so I have something's going on in the nucleus. And so what that happens is when a proton decays. Alright, so if you like H11, because hydrogen has an atomic number of 1, so what happens is that we get a proton decaying, and we end up with our positron, and because we've got a balance and have because we've got a balance and end up with the same got my numbers around the wrong way, got to have the same, so the atomic number's got to be a total of 1, which it already is, so this new particle has got to have an atomic number of 0. And then, of course, our mass number 1 there, it's 0 there, so this new particle's got to have so it's a neutron. Alright, and then this beta particle here, of course, shot out of the nucleus. Alright, so in your notes there it's going, so when a nucleus undergoes beta decay, the mass number stays the same, atomic number increases by 1, and then there's a equation there for it that's handy. When a nucleus undergoes beta positive decay, the mass number stays the same, the atomic number decreases by 1. Alright, so we've got an example. Okay, it says, what is the nuclide Y when AC undergoes beta decay according to the following equation? Alright, so this time they've given you an equation, and in that equation it's going to tell us what sort it is. Otherwise you need to be told whether it was beta positive or negative. So when we look at our equation, we can see here it's the electron one. So what do we know about Y? Alright, we know we've got to have a total of 89 atomic number. And so to get a total of 89, that'll be 90 minus 1 to give us 89. So our atomic number there is 90, and we've got a total mass of 228, and there's 0 there, so it's 228. So we look that up in our periodic table, and we find that is now thorium. Alright, so thorium has been the daughter nucleus. Alright, if there's a beta positive decay, right, so here's something that decays by beta positive. So beta positive decay, going back here, our beta positive, there we are. This is how we're going to represent it, plus 1, 0 and beta with the thing. So plus 1, 0, beta with the plus. So what do we got here? So then we know that that's got to be 80, and that's still 120, and we look up in our periodic table what 80 is, and we look up 80, and 80 is Hg. Alright, so there's a beta positive decay. So you just need to be told which sort of decay it is. Alright, last one. So the gamma ray. So gamma ray, it's usually occurs, usually occurs after alpha or beta. Alright, so it doesn't usually occur by itself. So what happens is that there's excess energy in the nucleus. and that excess energy is given off as a photon of light. Well, photon of light, photon of gamma, electromagnetic wave. All right, so it's like one of the theories is that there's certain energy levels in a nucleus, and there's excess energy. And so one of the examples of one of the things that does this is iodine 131. So iodine 131 is unstable, and so iodine 131 will decay to xenon 131 plus a beta particle and a gamma. Alright, so what happens is that when after the decay, there's excess energy in the nucleus of that xenon atom, which would be Xe, of that xenon atom, and then, so the beta particle, that's gone, excess energy in the xenon atom nucleus, and then that's given off as a photon of electromagnetic wave, which in this case is gamma. All right. So another way that you may see that written is that you've got your iodine, and then that decays to your xenon, so it's like it's a two-stage process. And then you have the 131 up here. But what they do is they put a little M, and that M means metastable, which means that it's almost stable. It's got a little bit of extra energy in there. So then what happens is that your metastable xenon becomes stable xenon with the emission of your gamma. All right, so yeah, that little M means there's extra energy still in the nucleus. All right, so there's others that do it. Cobalt 60, it says in your notes, and technetium 99, also in metastable states. All right, let's look at a couple of examples. All right, here's our first. We've got strontium 90. Decays by radio emission to form yttrium 90, and the equation is that. In this particular one, we see that, first of all, what's obvious is that there's a gamma is there as well. So part of it says find the atomic mass numbers for X and the type of radiation. All right, so I've got strontium 90. And it's going to yttrium 90. Then the atomic number, it's got to be a total of 38, so we're going to take one off and a 0 up there. So it's the masses are going to stay the same. So it looks like an electron, so a beta minus plus the gamma as well. All right, so what's emitted? A beta minus and a gamma are emitted according to that. All right, next example. Here we go. We've got iodine, a radioisotope superfrequency from fourth thyroid cancer, produced two-stage process. Firstly, tellurium 130, so that's 130 Te 52. Bombarded with neutrons inside. This results in the formation of very unstable tellurium 131 and a gamma ray. Write down a balanced nuclear equation for the process of creating. Alright, so I've already done part of it. So we start with what's on the left here. We bombard it, and then we get this and this. So the question is, what are we bombarding it with? So plus, well, we're something with a 0, because again, remember, our atomic numbers have got a balance. We already got 52 on both sides. But here we've got 131 mass numbers on the left and only 130, so it's got to have a mass of what? And then it's a neutron. So it's bombarded with neutrons anyway. So there's our equation. A pretty nice equation. Then part B says tellurium-131 decays by a beta electron emission producer daughter identify. Alright, so let's have a look. So 131, 52 Te by beta electron minus 10 E plus. Alright, so it's got to be 53, it's 131, and then we look up and we find that that is iodine 131. Alright. So the question comes about then, why unstable? Alright, so there's some videos, strong nuclear force, weak nuclear force, and the weak and the strong. So inside the nucleus, what have we got? We've got the strong nuclear force. We've got the weak nuclear force. And also, because there's charges in there, we've got electrostatic forces as well. Alright, so the electrostatic forces are going to repel because there's lots of positive charges there, and somehow these ones, we've got to hold it all together. And when you look at this table, and this is in your notes, right, so there's this diagram that's in your notes, and it's probably a little bit smaller here, but you notice there, and this is the ones we're interested in, those purple boxes are stable nuclei, and you notice, the line of stability that it talks about here is kind of this curve that goes around there. So this line here represents where you've got the same number of protons and neutrons just in there, so the numbers of protons and neutrons are the same. And you can see that for light nucleuses down the bottom here, that's pretty much even, but as you get further up, it looks like you need more neutrons to keep the thing stable. So it looks like there's some sort of balance between the numbers of protons and neutrons. So there needs to be some sort of balance in the forces by protons and neutrons. Alright, if you haven't got that balance right, then it will decay. And also, if you have a look, when we get right up, which is up high, up here, up to bismuth, which is right where that black line ends, right up the top here, about there somewhere. Everything after that is radioactive, so it looks like for those bigger nucleuses, higher than bismuth, which is atomic number is equal to 83, so 83 protons. It looks like that now the size of the nucleus is getting such that we can't get that balance. Alright, so in your notes there's a whole bunch of questions in your notes, the notes there, questions 7 through to 27, and then also some in your textbook as well, problem set 6.